Hello, well, welcome to College Physics 2. This is the second part in our course where we're going through a lot of details in college physics. And this is the general contents for the first course. We went through this first column, talking a lot about mechanics, thermodynamics, vibrations, and waves. And then we did this first chapter getting into electricity and magnetism. And now we're going to finish this off. There's going to be a bunch of different chapters on electricity, magnetism. Then we'll get into light and optics, and finally modern physics. So for this lecture, we're going to be going over topic number 16. And this gets into electrical energy and capacitance. And we're showing a variety of different examples of what capacitors looks like. Some of those you may have seen in one form or another. Maybe a lot of that was a little bit stuff that's internal to the devices that you might have. And so first of all, we'll do some reading questions, a review, and so you can be looking over these and see what you see what you think. And so first one, we'll have about 4 questions or so. So a positive charge in a universal electric field accelerates, gains 5 joules of kinetic energy. How does a charge potential energy change? And for the purpose of this lecture, I'm mostly just going to be walking through these fairly quickly, so I won't have a lot of discussion on this. And so the answer to this first one is it loses 5 joules. And so if you look into the chapter in the textbook, I highly recommend that you follow along in the textbook. You'll see that these charts and everything that we do are very tightly coupled with the textbook. So for the second question, A and B are both points on an equal potential surface. What is the potential difference between point A and B? And so the answer for this one is it is 0. Third question is, as one moves away from a positive point charge, the electric potential changes in the way that cannot be determined from the information given. And that's a question. And so the answer is that it decreases the further away you go. Now in terms of what is a way to quantify what capacitance is, and the best way among these is to really consider all of these as true. We have what it's measured in, and it's called farads. It's the ratio of the magnitude of the charge on either conductor of the capacitor to the magnitude of the potential difference between the conductors. And it's constant for a parallel plate capacitor. So for this one, to increase the capacitance of a parallel plate capacitor, you can, and the answer is, for the choices given, increase the area of the plates. The larger the surface area, the more capacitance you can have. And so for this last question, select the option that best describes a dielectric. And a dielectric is a non-conducting material. This is the thing that is placed between the 2 plates, and it can affect the amount of capacitance that you can have. So that's a quick set of questions that are useful for you as you're going through the reading. So let's get into the topic discussions. So in this topic, you will see that the potential energy concept is also useful in the study of electricity. Because the Coulomb force is conservative, we can define an electric potential energy corresponding to that force. We will also define an electric potential, the potential energy per unit charge, which corresponds to the electric field. Then we'll be able to begin analyzing electric circuits, starting with capacitors, which are devices that store electric energy. So that's going to be the major focus of this chapter. So in this figure, we are showing when a charge Q moves in a uniform electric field E from point A to point B, the work done on the charge by the electric force is Qx delta X. And so that's what we're describing here. And so as you recall, the work done by a conservative force F on an object only depends on the initial and final positions of the objects and only on the path taken between those 2 points. This means that a potential energy function exists, potential energy is a scalar quantity with the change in potential energy equal by definition to the negative of the work done by the conservative force as shown here. Both the Coulomb force law and the universal law of gravity are proportional to 1/r squared because they have the same mathematical form, and because the gravity force is conservative, the Coulomb force is also conservative. As with gravity, an electric potential energy function can be associated with this force. To see how this works, imagine a small positive charge placed at a point A in a uniform electric field E as shown in this figure. Let's assume for now that the electric field is constant and that the charge moves parallel to the field. As the charge moves from point A to point B under the influence of the electric field E, the work done on the charge by the electric field is equal to the part of the electric force QE acting parallel to the displacement times the displacement. In this expression, Q is a charge and EX is the vector component of E in the X direction, not the magnitude of E. So EX can be positive or negative depending on the direction of E. Notice that in the figure, EX is positive. The displacement can either be positive or negative. So continuing on, here we substitute our definition of electric work into the work energy theorem. The energy force is conservative, so the electric work depends only on the endpoints of the path A and B, not on the path taken. This means as the charge accelerates to the right in the figure, it gains kinetic energy and loses an equal amount of potential energy. So remember that the work done by a conservative force can be reinterpreted as the negative of the change in potential energy associated with that force. So the change in the electric potential energy of the system consists of an object of charge Q moving through a displacement delta X in a constant electric field as given by the equation here, where EX is the X component of the electric field and delta X displacement of the charge along the X axis. Even though the potential energy can be defined for any electric field, this equation is valid only for the case of a uniform, which means constant electric field for a particle that undergoes a displacement along a given axis. And here we call that the x-axis. Because the electric field is conservative, the change in potential energy does not depend on the path. So it doesn't matter if the charge stays on the axis all the time, the change in potential energy will be the same. So here we have another figure. And so in A, we see when the electric field E is directed downward, point B is at the lower electric potential than point A. And then in B, we have an object of mass M moving in the direction of the gravitational field G. So let's take a look at these two figures, which shows a comparison of the electric and gravitational fields. As you can see, both fields are directed downwards. We see that the positive charge in any field acts very much like mass in a gravity field. A positive charge at point A falls in the direction of the electric field, just like a positive mass falls in the direction of the gravity field. So let's point B to the 0 point for potential energy in both figures. For conservation of energy, in falling from point A to point B, the positive charge gains electric energy equal in magnitude to the loss of electric potential energy. The absolute value sign on Q are there to make it explicit that the charge is positive in this case. In a similar way, the mass in the right-hand figure gains kinetic energy in magnitude to the loss of gravitational potential energy. So for positive charges, you can see that electric potential energy works very much like gravitational potential energy. In both cases, moving an object opposite the direction of the field results in a gain of potential energy. And when the objects are released, the potential energy is converted to the object's kinetic energy. So then as we finish up on this particular topic, one major difference between electric and gravitational potential energy is that there are two kinds of electrical charges, positive and negative. But gravity has only positive gravitational charge or mass. a negative charged particle at rest at point A in the figure would have to be pushed down to point B. To see why, let's apply the work energy theorem to a negative charge at rest at point A and assume to have some speed v on arriving at point B. Notice that the negative charge has a positive charge in electric potential energy and moving from point A to point B. If the negative charge has any speed at point B, the kinetic energy corresponding to that speed is also positive. Because both terms on the right-hand side of the work energy equation are positive, there is no way of getting the negative charge from point A to point B without doing positive work W on it. In fact, if the negative charge is simply released at point A, it will, quote, fall upward against the direction of the field. So let's have a question to think about this. So if an electron is released from rest in a uniform electric field, the electric energy, potential energy of the charged field system, and the answer to this is decreases. And the reasoning for that is the field exerts a force on the electron, causing it to accelerate in the direction opposite to that of the field. In this process, electric potential energy is converted into kinetic energy of the electron. Note that the electron moves in a region of higher potential, but because the electron has negative charge, this corresponds to a decrease in the potential energy of the electron. Okay, let's talk about electrical potential. So let's define electrical potential difference delta V between points A and B as the charge in electric potential energy as a charge Q moves from A to B, defined by the charge Q relative to the potential energy. Because the electrical potential energy is a scalar quantity, electric potential is also a scalar quantity. From this equation, you can see that electric potential difference is a measure of the change in electric potential energy per unit time. You can also think of the electric potential differences as a work per unit charge that would have to be done by some force to move a charge from point A to point B in the electric field. So take a look at the units. 1 joule of work must be done to move a 1 coulomb charge between 2 points that are at a potential difference of 1 volt. In the process of moving through a potential difference of 1 volt, the 1 coulomb charge gains 1 joule of energy. For the special case of a uniform electric field, like the field between charged particle plates, we can divide our potential energy equation by Q to get the equation shown here. The result shows that the potential difference also has units of electric field times distance. That means that the SI unit of the electric field, the Newton per Coulomb, can also be expressed as volts per meter. Remember that this equation for delta Vx is valid only for a system consisting of a uniform electric field and a charge moving in one dimension. Released from rest, positive charge accelerates spontaneously from regions of high potential to low potential. If a positive charge is given some initial velocity in the direction of high potential, it can move in that direction, but will slow and finally turn around, just like a ball tossed upward in a gravity field. Negative charges do exactly the opposite. Released from rest, they accelerate from regions of low potential towards regions of high potential. Work must be done on negative charges to make them go in the direction of lower potential energy, lower electric potential. So here is another question for us to be thinking about, what we just talked about. If a negatively charged particle is placed at rest in an electric potential field that increases in the positive x direction, the particle will, the answer is accelerate in the positive x direction. The reasoning is that the electron, a negatively charged particle, will move towards a region of higher electrical potential. Because of the electron's negative charge, this corresponds to a decrease in the electrical potential energy. Here's another one to think about. The figure below is a graph of the electric potential as a function of position. If a positively charged particle is placed at point A, what will its subsequent motion be? and it will, and the answer is go to the left. So charged particles always tend to move towards the position of lower potential energy. The electrical potential energy of a charged particle is PE equals QV. And for positive charged particles, this decreases as V decreases. Thus, a positive charged particle located at X equals A would move towards the left. So continuing on, here's another question. If a negative charged particle is placed at point B in the figure below, given a very small kick to the right, what will its subsequent motion be? And the answer is it will oscillate around point B. The reason is for a negatively charged particle, the potential energy PE equals QV decreases as V decreases. A negative charged particle oscillates around X equals B, which is a position of minimum potential energy for negative charges. So in this figure, we're showing a car battery. I'm sure you guys have seen something like this. And so this is something that has a common application and with the potential differences. The 12-volt battery is the potential that's used in a car. A car battery maintains a potential difference across its terminals, with the positive terminal 12 volts higher in potential than the negative terminal. In practice, the negative terminal is usually connected to the metal body of the car, which can be considered to be a potential of 0 volts. The battery provides the electrical current necessary to operate headlights, a radio, power windows, and motors. Think about a charge of 1 coulomb to be moved around a circuit with a battery and a couple of these external devices. As the charge is moved inside the battery from the negative terminal, which is at 0 volt, to the positive terminal, which is at 12 volts, the work done on the charge by the battery is 12 joules. Each coulomb of positive charge that leaves the positive terminal of the battery carries an energy of 12 joules. As a charge moves through the external circuit towards the negative terminal, it gives up 12 joules of electrical energy to the external device. When the charge reaches the negative terminal, its electrical energy is 0 again. At this point, the battery takes over and restores 12 joules of energy to the charge as it moved from the negative to the positive terminal, which allows the charge to make another transit of the circuit. So let's now talk about electrical potential and potential energy due to point charges. So in the figure, we're showing an electric field and electric potential versus distance from a point charge of 1.11 times 10 to the minus 10 coulombs. Note that V is proportional to 1 over R, where E is proportional to 1 over R squared. So talking about this picture and what we're trying to describe in this section, as you have seen so far, we often define a point of 0 electric potential by grounding or connecting to the earth, some point in the circuit. For example, if the negative terminal of a 12-volt battery were connected to ground, it would be considered to have a potential of 0, and the positive terminal would have a potential of plus 12 volts. This potential difference is only locally defined. Now we turn our attention to the electric potential of a point charge. As you know, the electric field of a point charge extends throughout space, so its electric potential does too. The 0 point of an electric potential could be taken anywhere, but it's usually taken to be an infinite distance from the charge, far from its influence and the influence of any other charge. So the electric potential created by a point charge Q at any distance r from the charge is given by the equation shown here. From the equation, you can see that the electric potential or work per unit charge requires to move a positive test charge in from infinity to a distance r from a positive point charge Q increases as the test charge moves closer to Q. The plot of the equation shows that the potential associated with a point charge decreases as 1 over r with increasing r. Remember that the magnitude of the charge electric field decreases as 1 over r squared. The electric potential of 2 or more charges is obtained by applying the superposition principles. The total electric potential at some point B due to several point charges is the algebraic sum of the electric potentials due to the individual charges. Because electrical potential is a scalar quantity, it's much easier to evaluate the electrical potential at some point due to several charges than to evaluate the electric field, which is the electric quantity. So here in this figure, we're showing the electrical potential, which we're having in terms of some arbitrary units in a plane containing an electric dipole. Potential is plotted in the vertical dimension. So the figure is a computer-generated plot of the electric potential associated with an electric dipole, which consists of two charges of equal magnitude but opposite in sign. The charges lie in horizontal planes at the center of the potential spikes. The value of the potential is plotted in the vertical dimension. The computer program has added the potential of each charge to arrive at total values of the potential. So let's talk about potential energy and potential energy due to point charges. In the figure, we have the electric potential V1 at P due to the point charge Q1 is V1 equals KE Q1 R. And so that's in figure A. And then in figure B, if a second charge Q2 is brought from infinity to P, the potential energy of the pair is PE equals KE Q1 Q2 R. So let's look at the relationship between electric potential and electric potential energy. If V1 is the electric potential due to charge Q1 at point P, as in the figure on the left, the work required to bring charge Q2 from infinity to P without acceleration is Q2 V1. By definition, this work equals the potential energy of the two particle system when the particles are separated by a distance r, as shown in the figure on the right. So we can express the electrical potential energy of the pair of charges as shown in the equation in the right-hand figure. If the charges are of the same sign, PE is positive because like charges repel, positive work must be done on the system by the external agent to force the two charges near each other. On the other hand, if the potential charges are of opposite sign, the force is attractive and PE is negative. This means that the negative work must be done to prevent unlike charges from accelerating towards each other as they are brought close together. So here's another question for us to consider. Consider a collection of charges in a given region, and suppose all of the charges are distant and have a negligible effect. Further, the electric potential is taken to be zero at infinity. If the electric potential at a given point in the region is zero, which of the following statements must be true? And so you can be thinking about that for a while. You can pause the recording, but the answer is D, only. So what that means is if the potential is zero at a point located a finite distance from the charges, negative charges must be present at the region to make negative contributions to the potential and cancel positive contributions made by the positive charges in the region. Here's another one. So a spherical balloon contains a positive charged particle at its center. True or false? So you can think about that as the balloon is inflated to a larger volume while the charged particles remain at the center. Which of the following is true? And the answer is the electric flux through the balloon remains the same. Both the electric potential and the magnitude of the electric field decrease as the distance from the charged particles increases. However, the electric flux through the balloons does not change because it is proportional to the total charge enclosed by the balloon, which does not change as the balloon increases in size. So one thing, again, that's really helpful in the textbook and what we have with these lecture notes is we have these problem-solving strategies. And so keep this in mind. And I like to say always the first thing you want to do is after you read the problem carefully is you want to draw a diagram of all that gives you the information you need to solve. So in this case, we want a diagram of the charges and circle the points of interest. Number 2, calculate the distance from each charge to the point of interest, labeling it on the diagram. And for each charge Q, calculate the scalar quantity V. The sign of each charge must be included in the calculations. That's important. So sum all the numbers found in the previous steps of obtaining the electric potentials at the point of interest. So let's talk about potentials and charge conductors. From the work equation, we see that work done on a charge by electric forces is related to the change in electric potential energy of the charges. From the potential energy equation, we see that the change in electric potential energy between 2 points A and B is related to the potential difference between those points. So we can combine these two equations and notice what this means. No net work is required to move a charge between 2 points that are at the same electrical potential. In mathematical terms, the result says that W equals to 0 whenever VB equals to VA. Okay, so in this figure, we have an arbitrary shaped conductor with an excessive positive charge. When the conductor is in electrostatic equilibrium, all the charges reside at the surface, E equals 0 inside the conductor, and the electric field just outside the conductor is perpendicular to the surface. The potential is constant inside the conductor and is equal to the potential at the surface. Remember when we talked about a conductor is in electrostatic equilibrium in the last topic, you learned that a net charge placed on a conductor is entirely on its surface. Also, we showed that the electric field just outside the surface of a charged conductor is in electrostatic equilibrium is perpendicular to the surface, and that the field inside the conductor is 0. Now let's show that all points on the surface of a charged conductor in electrostatic equilibrium are at the same potential. Take a look at the figure here. The black line connects point A and B on a charged conductor. We can assume that the charge on the conductor are in equilibrium with each other, so none are moving. In this case, the electric field is always perpendicular to the displacement along the path. This has to be the case, or part of the electric field tangent to the surface would move the charges. Because E is perpendicular to the path, no work is done by the electric field if a charge is moved between the given 2 points. From our equations for the work, you can see that if the work done is 0, the difference in electric potential is also 0. This means the electric's potential is a constant everywhere on the surface of a charged conductor in equilibrium. Because the electric field inside a conductor is 0, no work is required to move a charge between 2 points inside the conductor. Our equation tells us that if the work done is 0, the difference in electric potential between any 2 points inside a conductor must also be 0. We can conclude that the electric potential is constant everywhere inside a conductor, and since one of the points inside the conductor could be arbitrarily close to the surface, we can say that the electric potential is constant everywhere inside a conductor and equals to the same value at the surface. So what this tells us is that no work is required to move a charge from the interior of a charged conductor to its surface. Keeping in mind, though, that the potential inside a conductor is not necessarily 0, even though the interior electric field is 0. So it's a simplifying approximation that's useful for consideration. So now is a good time to introduce a new unit, an energy unit, which is considered commonly used in atomic and nuclear physics as the electron volt, or EV. So for example, electrons in normal atoms typically have energies of tens of EVs. Excited electrons and atoms emitting X-rays have energies of thousands of EVs, and high energy gamma rays, electromagnetic waves emitted by the nucleus have energy of millions of EVs. The electron volt is defined as the kinetic energy that an electron gains when accelerated through a potential difference of 1 volt. Here's another question to be considering. So an electron initially at rest accelerates through a potential difference of 1 volt, gaining kinetic energy KEE, while a proton also initially at rest accelerates through a potential difference of -1 volt, gaining a kinetic energy of KEP. Which of the following relationships hold? And the answer is KEE is equal to KEP. So both of these quantities here are equal. So I'm going to just pass on giving some more descriptive information on that. You can see the textbook for more details. So let's talk about equipotential surfaces. So in the figure, we're showing electropotential surfaces with the dashed lines here and electric field lines. And so the dashed blue lines are electric potential, equipotential, and the orange lines are the electric field lines. So for A, a positive point charge is what we're showing, and for B, we're showing 2 point charges of equal magnitude and opposite signs. In all cases, the electropotential are perpendicular to the electric field lines at every point. So an equal potential surface is a surface where the potential is the same at all points, which means that the potential difference between any 2 points on an equal potential surface is 0. So no work is required to move a charge at constant speed on an equal potential surface. Also, the electric field at every point of a equal potential surface is perpendicular to the surface. If the electric field has a common component parallel to the surface, that component would produce an electric force on a charge placed on the surface, which would do work on the charge as it moved from one point to another. This is a contradiction to the definition of equipotential surface. We can represent equipotential surfaces by drawing equipotential contours, which are two-dimensional views of the intersections of the equipotential surfaces with the plane of the drawing. Like in the figure shown here, we generally refer to equipotential contours simply as equipotentials. In the figures, notice that the equipotentials shown in blue are perpendicular to the electric field lines, which are shown in orange. Our relationship for the potential of a single point charge shows us that the potential is constant on any surface on which R is constant. That means the equal potential of a point charge are in a family of spheres centered on the point charge, as you can see in the figure on the left. The figures on the right shows the equipotentials associated with two charges of equal magnitude but opposite signs. So this is a figure of an electrostatic precipitator. And so on the left, we see a schematic diagram. This is an A of an electrostatic precipitator, and it compares the air. And what we want to be doing is compare the air pollution when the precipitator is operating and when it is turned off. An electrostatic precipitator is a device that removes particulate matter from a combustible gases, which is used to reduce air pollution. It's especially useful in coal burning power plants and in industrial operations that generate large quantities of smoke. Systems currently in use can eliminate approximately 90% of the mass of ash and dust from smoke. Unfortunately, a very high percentage of the lighter particles still escape, and they contribute significantly to smog and haze. The figure on the left illustrates a basic idea of the electrostatic precipitator. A high voltage, typically 40 kilovolts to 100 kilovolts, is maintained between a wire running down the center of a duct and the outer wall, which is grounded. The wire is maintained at a negative electric potential with respect to the wall, so the electric field is directed towards the wire. The electric field near the wire reaches a high enough value to cause a discharge around the wire and the formation of positive ions, electrons, and negative ions. The electrons and negative ions are accelerated towards the outer wall of the non-uniform electric field and collide with the dirt particles in the gas. these particles become charged through collisions and ion capture. Because most of the charged dirt particles are negative, they are also drawn to the outer wall by the electric field. The duct can be shaken so that the particles fall loose and are collected at the bottom. The electrostatic precipitator also recovers valuable metal oxides from the stack. So there's just more information here you can read in the text, but I think that's enough to give you a perspective of what we're trying to talk about. Here we're showing you a zero graphic process, and there's several steps. And A is the photoconductive surface is positively charged. B, through the use of a light source and a lens, a hidden image is formed on the charged surface in the form of positive charges. C, the surface containing the image is converted with a negative charge powder, which adheres only to the image area. D, a piece of paper is placed over the surfacing given a charge. The transfer, this transfers the image to a paper, which is then heated to fix the powder to the paper. The image on a drum of a laser printer is produced by turning a laser beam on and off as it sweeps across the silicium coated drum. So this is a process that also applies towards electrostatic charges. So here we're just seeing an example of how that would work. And once again, I'll refer you to the textbook for some more details. Okay, well, let's talk a little bit more in detail about capacitors. And so in the figure, we're showing a parallel plate capacitor which consists of two parallel plates, each of area A, separated by a distance d. A capacitor is a device used in many different electric circuits, for example, to tune the frequency of radio receivers, eliminating sparkling in automobile ignition systems, or store short-term energy for rapid release in electronic flash units. And so the figure shows a typical design for a capacitor. And you can see that it's hooked up to a battery to give, that's charging up the capacitor. So the capacitance C of a capacitor is a ratio of the magnitude of the charge on either conductor or plate to the magnitude of the potential difference between the plates. In this equation, the quantities Q and delta V are always taken to be positive. And so we can do a quick example, and that's what we're showing in the bottom here. Let's say that we have a 3 microfarad capacitor is connected to a 12-volt battery. Using our equation, we find that the magnitude of the charge on each plate of the capacitor is 36 microcoulombs. From this equation, you can see that a large capacitance is needed to store a large amount of charge for a given applied voltage. A farad is a very large unit of capacitance. In practice, most typical capacitors have capacitance ranging from microfarads to picofarads. So the capacitance of a device depends on the geometric arrangement of the conductors. The capacitors of a parallel plate capacitor with plates separated by air, as shown in the figure, can be easily calculated from 3 facts. First, the magnitude of the electric field between the two plates is given by the relationship where rho is the magnitude of the charge per unit area of each plate. Second, the potential difference between the two plates is delta V, where D is the distance between the two plates. And third, the charge on one plate is given by the relationship where A is the area of the plate. We can substitute into the definition of capacitance and now cancel the charge per unit area rho. And we have a result here where A is the area of one of the plates, D is the distance between the plates, E naught, epsilon naught is the permittivity of free space. From our result, we can see that the plates with large enough areas can store more charge. The same is true for a small plate separation D, because then the positive charge on one plate exerts a strong force on the negative charge on the other plate, allowing more charge to be held on the plates. So in this figure, we're showing the electric field between the plates of a parallel plate capacitor is uniform near the center, but non-uniform near the edges. The figure shows the electric field lines of a more realistic parallel plate capacitor. Note that the electric field is very nearly constant in the center of the plates, but becomes less so when you get towards the edges. Here we're showing an illustration of a type of keyboard. And so the capacitance of the parallel plate capacitor increases as the plate spacing decreases. The substance labeled dielectric is an insulating material as described in a later section. Computers use capacitors. For example, one type of computer keyboard has capacitors as the basis of its keys. And so we're getting a chance to see how that would look here. As you press the key, it's engaging and it's changing the capacitance. And so keep that in mind as one application. Here are some symbols, and you will be seeing some types of circuits. And so we're seeing the schematic symbol for a capacitor, a battery. It can kind of look a little bit like that, but you don't have them at the same size on both sides. One is longer than the other. A resistance looks like a squiggly line, and then you have a light bulb, or that's what you would have for a light bulb, and a diode is not quite the same, but we're just showing the symbol for a light bulb here. So now we can see how we're drawing electric circuits, and you can see what would look in a more realistic view. And here we're seeing it, what the equivalent would be for a circuit. So we start at the positive term of the battery. We come first to a junction with a light bulb. If we follow the path through that bulb, we encounter a resistor. And if we follow the other path, we encounter another light bulb. Both paths reconnect and end up at a negative terminal of the battery. So we're showing that one that this light bulb will not end up shining as bright because the resistance reduces the amount of electricity flow versus this other one. Here we're showing capacitors in parallel. We can combine capacitors and circle in different ways, but most reduce to two simple configurations called parallel and series. The goal is to find the single equivalent capacitance due to the combination of several different capacitors that are in parallel or in series with each other. First, we look at two capacitors connected as shown in the figure. They are said to be in parallel. The left plate of each capacitor is connected to the positive term of the battery by a conducting wire. So the left plates are in the same potential. In the same way, the right plates are connected to the negative terminal battery are also in the same potential. This means that the capacitors in parallel both have the same potential difference across them. So we're showing some equations that help us see what we can do when we evaluate things that are in parallel. And so when the capacitors are first connected in the circuit, electrons are transferred from the left plate through the battery to the right plate, leaving the left plates positively charged and the right plates negatively charged. The energy source from the transfer of charge is the internal chemical energy stored in the battery, which is converted to electrical energy. The flow of charge stops when the voltage across the capacitors equals the voltage of the battery. This is when the capacitors have their maximum charge. If the maximum charge on the two capacitors are Q1 and Q2, the total charge Q stored by the two equations is the sum of the charges. So C1 plus C2. This means that we can replace the two capacitors with one equivalent capacitor having a capacitance of the C equivalent, as you can see in the figure on the right. This equivalent capacitor must have exactly the same external effect on the circuit as the original two, so it must store Q units of charge and have the same potential difference across it. So from what you can see that the equivalent capacitance of parallel combination of capacitors is larger than any of the individual capacitances. So now we're showing them in series. For a series combination of capacitors, the magnitude of the charge must be the same on all plates. So So regardless of how many capacitors are in series or their capacitances, all the right plates gain charge of minus Q, and all the left plates have a charge of Q. This corresponds to the conservation of charge. So there's more details in the textbook. I'm just going to skip over that for now. So we can see that after an equivalent capacitor for a series of capacitors fully charged, the equivalent capacitor must end up with a charge of minus Q on its right plate and a charge of plus Q on the left plate. Let's apply the definition of capacitance to the circuit with the equivalent capacitance shown on the right, where delta V is the potential difference between the battery terminals. We can write the potential difference across each capacitor. From the figure on the left, we see that the battery voltage is just the sum of the voltages, where delta V1 and delta V2 are the potential differences across the capacitors C1 and C2, which is correspondence to the conservation of energy. You can see that the potential difference across any number of capacitors or other circuit elements, for that matter, in series equals the sum of the potential difference across the individual capacitors. Let's use this fact to write the voltages in terms of charge and capacitance. Cancels Q, and the result is a relationship among the capacitors in series in the equivalent capacitance. We can, of course, extend this analogy to any number of capacitors connected in series. So here we have an equation for series combination of capacitors, and we can get the equivalent as we're showing here. And so thus the equivalent capacitance of series combination is always smaller than any individual capacitance in the combination. So here is a question for us to think about here. A capacitor is designed so that one plate is large and the other is small. If the plates are connected to a battery, the answer for this one is the plates have equal but opposite charge. And you can see that the textbook for some more details about that. Here is another problem-solving strategy for complex capacitor combinations. And so the first thing you want to do is combine capacitors that are in series or in parallel, follow the derived formulas. We talked about those already. Redraw the circuit after every combination. Repeat the first two steps until there is only a single equivalent capacitor. Find the charge on the single equivalent capacitor using the equation shown. Work backwards through the diagrams to the original one. Find the charge and voltage drop across each capacitor along the way. And so to do this, we look at the capacitor equation, the equation for capacitors in parallel. The capacitors in parallel all have the same voltage differences as does their equivalent capacitors. And the equations for capacitor in series, we have that you're seeing there, and the capacitors in series all have the same charge, as does their equivalent capacitor. So those are just a few tips on how to solve complex capacitor combinations. So what is the energy in a capacitor? As you know now, a capacitor can store energy if the plates of a charged capacitor are connected by a conductor like a wire, for example. Charge transfers from one plate to the other until both plates are uncharged. Sometimes you can see this discharge as a visible spark. That's what we're showing in this figure. If you accidentally touch the opposite plate of a charged capacitor, your fingers would act as a pathway and you would get an electric shock. When high voltages and large quantities of charge are present, as in a power supply of a television set, such a shock can be fatal. So it's something to be careful. So here we're showing a plot of voltages versus charge for a capacitor in a straight line with slope 1/c. The work required to move a charge of delta Q through a potential difference of delta V across the capacitor plate is delta W equals delta V times delta Q, which equals the area of the blue rectangle, which is highlighted there. The total charge required to charge the capacitor to a final charge of Q is the area under the straight line, which equals delta Q delta V over 2. So capacitors store energy, and that energy is the same as the work required to move the charge onto the plates. If the capacitor is initially uncharged, meaning both plates are neutral, the plates are at the same potential then very little work is required to transfer a small amount of delta Q from one plate to another. Once this charge has been transferred, a small potential difference appears between the two plates, so the work must be done to transfer additional charge against the potential differences. As we know, W is also the electric charge stored in the capacitor. From the definition of the capacitance, we have Q equals C delta V, so we can express the energy stored in a capacitor three different ways. We have an example here, and this is some stuff that is also in the textbook. So we're just showing a quick example of how we could play this out. In practice, there is no limit to the maximum energy or charge that can be stored in a capacitor. At some point, the Coulomb forces between the charges of the plates become so strong the electrons actually jump across a gap, discharging the capacitor. For this reason, capacitors are usually labeled with a maximum operating voltage, so something to keep in mind. Maybe you've seen a defibrillator. This is an example that uses large capacitors. They get charged up before it's actually released, and hopefully helping the patient to have their heart to start beating again. So that's just a little bit of an example of a practical application of how this would work, how this would be used. So here's a couple of think and review questions. And so for this one, a parallel plate capacitor is disconnected from a battery and the plates are pulled a small distance apart. Does Q increase, decrease, or stay the same? And the answer for this is Q stays the same. And so I'm just going to go through these quickly, and you can review them at your leisure. This next one, parallel plate capacitor is disconnected from a battery and the plates are pulled a small distance farther apart. Does C increase, decrease, or stay the same? And the answer is decrease. Parallel plate capacitor is disconnected from a battery and the plates are pulled a small distance from farther apart. Does E between the plates increase, decrease, or stay the same? And the answer is E, the electric field stays the same. A parallel plate capacitor is disconnected from a battery and the plates are pulled a small distance apart. Does delta V increase, decrease, or stay the same? And the answer is delta V increases. Once again, for the same question, does the energy stored in the capacitor increase or decrease or stay the same, pulling them apart? And the answer is the potential energy increases. So let's now talk about this dielectric, a material that you can be putting to the plates, and what is the advantage of doing that. And dielectric is an insulating material, for example, rubber, plastic, or wax paper. When a dielectric is inserted between the plates of a capacitor, the capacitance increases. If the dielectric completely fills the space between the plates, the capacitance is multiplied by a factor kappa called the dielectric constant. And so this is a way of how you can be, for the same size of a capacitor, you can have greater capacitance. And there's more details in the textbook that you can review to find out more about this. Here is just a list of the dielectric constant for the various types of materials that are used in capacitors. And so you can take a look at that at your leisure. This is also in the textbook. Here we're showing in the figure a dielectric breakdown in air. Sparks are produced when a large alternating voltage is applied across the terminals by high voltage in induction coil power supply. So here we're showing it's basically it's a dielectric breakdown of air. So the air itself is acting as a conductor in this example. Here are some examples of commercial designs for a capacitor. You can have a rolled capacitor, that is one, and so you can have that. You can have a high voltage capacitor consisting of many parallel plates separated by an insulating oil. So you can have an oil capacitor, a rolled capacitor. And finally, you have an electrolytic capacitor is the one on the far right in figure C. So these are just different examples of ways of, for different application. One is more beneficial than another. And here we're also seeing another example of a capacitor with a large number of plates of what you're seeing on the right. So some more questions here. I'm just going to quickly go through these. So you can read through these at your leisure, but the answer for this first one is C. C increases. The next question here is Q increases. That's the answer for this question. This one, the answer is E stays the same. You can look that over at your leisure. This one, delta V stays the same. That's the answer for this question. And finally, for this question, the potential energy PEC increases. So for this next topic, we have an atomic description of dielectrics. And so maybe you might be wondering why a dielectric increases the capacitance of a capacitor. For an explanation, you would need to look at the atomic description of the material. So this is something that's spelled out in the text, so I'll just kind of give a rough sketch. So you would need to understand the property of some molecules called polarization. A molecule is said to be polarized when there is a separation between the average positions of a negative charge and its positive charge. Some molecules, such as water, this condition is always present. So you can, anyway, I'm just going to skip over that. But so there's this concept that we're dealing with here, and it's called polarization. And polarization is what enables the ability to have a capacitor. So in the figure in A, we're seeing a symmetric molecule that has no permanent polarization. In the bottom, we're having an external electric field induced to polarization in the molecule. So it has the ability to store charge. So a symmetric molecule like the one on the top does not have a permanent polarization, but a polarization can be induced if it is in an external electric field. So this is called an induced polarization, and is a main effect for most materials that are used as dielectrics and capacitors. Here we're just showing some more details of how this would work. The polar molecules are randomly oriented in a dielectric. That's an A. B, we're seeing an electric field is applied to the dielectrics, and you can see how it's starting to get ordered. And the charged edge of the dielectrics acts as an additional pair of parallel plates, reducing the overall field between the actual plates. The interior of the dielectric is still neutral. So that gives a nice description of the capacitance. Here's a few more questions to think about. And so I'm just going to give you the answers, and you can review these at your leisure. So for this, the answer is C, increases. For this next chart, the answer is C. And so that's the answer for that. And then now we have the assess, seeing to learn. And once again, I'm just going to give the answer. You can read these over and pause during the video, and you can go over them in more detail. So for this first one, the answer is none of the above. For the second one, the answer is A. For this one, the answer is EA is equal to EB. For this fourth one, the answer is true. For this fifth one, the answer is number 2. For the sixth one, the answer is number 5. For this next one, number 7, the answer is none of the above. For here in this one, number 8, the answers are 1, 2, and 4 are true. For 9, the answer is number 4. For 10, the answer is number 4. And for 11, the answer is delta V decreases, Q stays the same, and U decreases. with that, we're just going to have a couple of summary charts. So we'll spend a little bit more time going over this and then we'll finish. So for electric potential energy and electric potential, the change in the electric potential energy of a system consists of an object of charge Q moving through a displacement delta X at a constant electric field E is given by the equation shown, where E sub X is the component of the electric field in the X direction and delta X equals XF minus XI. The difference in electric field potential between 2 points A and B is delta V, where delta PE, delta potential energy, the change in electric potential energy as a charge Q moves between A and B. The units of potential difference are joules per coulomb or volts, and thus 1 joules per coulomb is equal to 1 volt. The electric potential difference between 2 points A and B is a uniform electric field E, is shown here, where delta X is the displacement between A and B, and E sub X is the X component of the electric field in that region. The electric potential and potential energy of point charges, the electric potential due to a point charge Q at distance R from the point charge is given here. The electric potential energy of a pair of point charges separated by a distance R is given in the second equation. These equations can be used in the solution of conservation of energy problems and in the work energy theorem. So for potential charged conductors and equal potential surfaces, every point on the surface of a charged conductor in electrostatic equilibrium is at the same potential. Further, the potential is constant everywhere inside the conductor and equals its value on the surface. The electric volt is defined as the energy that an electron or proton gains when accelerated through a potential difference of 1 volt. Conversion between electron volts and joules is shown here. For capacitors, a capacitor consists of 2 metal plates with charges that are equal in magnitude but opposite in sign. The capacitance C of capacitor is the ratio of the magnitude of the charge Q on either plate to the magnitude of potential difference, delta V, between them. Capacitance has units of coulomb per volt or farads. The capacitance of a parallel plate capacitor is given by the equation where epsilon naught, epsilon 0 is a constant called the permittivity of free space. And for combination of capacitors, the equivalent capacitance of a parallel combination and a serial combination, the capacitors can be found using the equations shown. So parallel, they add. Series, you have to do 1 over each one of them. Those add in that manner. Problems involving a combination of capacitors can be solved by applying these equations repeatedly to the circuit diagram, simplifying it as much as possible. The steps is followed by working backwards to the original diagram, applying C equals Q over delta V, that parallel capacitors have the same voltage drop and the series capacitors have the same charge. For energy in a capacitor, these are shown are 3 equivalent expressions for calculating the energy stored in a charged capacitor. And for capacitors with dielectrics, when a non-conducting material called a dielectric is placed between the plates of a capacitor, the capacitance is multiplied by the factor kappa, which is called the dielectric constant, a property of the dielectric material. The capacitance of a parallel plate capacitor filled with a dielectric is given here. Okay, well, that's it for this lecture. Thank you very much.